Welcome to Session 7 of Dr. Wheeler's Understanding SPC seminar, where we come to the heart of the matter. The use of the within subgroup variation, Method 2, is one of the foundations of process behavior charts. Since this method assumes that the data are homogeneous within the subgroups, we have to talk about rational subgrouping and the related topic of rational sampling. As the word rational implies, this foundation for the charts requires judgment as we match the context for the data with the structure of the process behavior chart. This session will use Chapter 5 of the Understanding SPC text, where we begin on page 90 with the rules for detecting potential signals with a process behavior chart.
We're now talking about detecting process changes. And I'm going to give you a pattern detection guideline. Any pattern that repeats itself 8 times in a row is not random. It's not routine variation. There's something systematic going on. A 2-point, a 3-point, a 4-point pattern keeps repeating. Go find out why. Here on page 891, you have a range chart. 3 workers were mixing rubber, and they had samples from each worker, subgroup size 5. This is the range chart from the average and range chart. And they took it down and showed it to the supervisor. So you've got a problem with operator 1. You've got a high, low, low pattern that repeats itself 8 times in a row here. Find out what's going on with operator 1. The supervisor said, he's my best man. He's conscientious, 30 years experience. I wish I had a whole plant like him. Oh, no, you don't. He's not getting the rubber mixed. Too much variation. So I went out to watch, and yeah, operator 1 dropped the rubber into the mixer and then stepped back. His cataracts had gotten so bad he couldn't see how to do the job anymore. They had a blind man running a rubber mill. And a rubber mill is a very hazardous piece of equipment. Next page, you have a thickness for a sheet of vinyl. And so he's tracking the thickness at one location, 10 inches from the edge of this sheet of vinyl that's going to be used for the skin of a dashboard for an automobile. And he said to me, I recognize a sine wave when I see one. On a hunch, I reached over and turned off the automatic thickness controller, and I continued to collect my data. We have an automatic thickness controller here that's holding the average by weaving back and forth. Do not drive home this way. But officer, on the average, I was in the right lane. Won't cut it. You see, the automatic thickness controller is doubling the variation. And because of the variation, I watched the next step create 100% scrap for 2 hours one day. Variation creates cost. In both of these, it's the interpretation of the charts and their context that led to the discoveries. This alertness for patterns which fit in with the way the data are collected and plotted cannot be programmed. It depends upon someone taking the time to think about and to look at and think about the charts. This has always been and will always be an essential part of the effective use of process behavior charts. The process behavior charts are the interface between your data and your brain. And until the brain's engaged, nothing happens. Now, your software is going to have all kinds of detection rules. The most commonly and widespread use of the detection rules, the most commonly used, are the Western electric zone tests. Of course, they start off with a point outside the limits. Duh, that's been there forever. And then the next 3 rules are run tests. You have to have the order, the sequential order has to make sense to use a run test. But whenever 2 out of 3 successive values are both on the same side of the central line, or both are more than 2 sigma units away from the central line, look for causes of an intermediate size shift in the underlying process. Detection rule 3, 4 out of 5, more than 1 sigma away from the central line on the same side. And rule 4, 8 in a row on one side of the central line, although Nelson says 9 in a row. So 8, 9, or 10. Another guy, Assad said 8, 9, or 10, take your choice. So 8, 9, or 10 points in a row on the same side of the central line, that's a signal of a small but sustained shift. You can go overboard with detection rules. Many detection rules have been proposed. You should be very careful about using more than the 4 posted above. These 4 are a coherent set and will essentially maximize the power of the process behavior chart. As you add additional detection rules to this set of 4, you will be increasing the chance of a false alarm more than you will be influencing the sensitivity of the chart. That is why I suggest that you turn off all your detection rules in your software. Process behavior charts are the interface between your mind and your data. Process behavior charts allow you to detect changes in patterns, and they allow you to communicate these changes to others. All the computations, all the detection rules, and all the graphs are merely aids to help you to do this job of discovery and communication. Keep it simple. Now I want to show you what happens with the power, what these detection rules do. This comes out of a paper that Rip Stoffer and I did together, but I want to explain the graph a little bit. Here is the probability of detecting a shift in location within 10 subgroups of when it happens. Probability is from 0 to 100%. Horizontal scale, size of shift in standard units. Shifts of less than 1.5 standard errors are small shifts. They're going to be hard to detect, but they have very little impact upon the process stream, so they rarely will be worthwhile to identify and react to these shifts. Intermediate size shifts between 1.5 and 2.5 standard errors are easier to detect, moderate impacts upon the process stream, and occasionally will be worthwhile to identify and react to these shifts. Large shifts, easy to detect, bigger than 2.5 standard errors, large impacts upon the process stream, almost always worthwhile to economically to identify and react to these shifts. These are the ones you want to find. These are the ones you really don't care about. Here are the power functions. Here are the power function curves. This first curve is rule 1 alone. With rule 1 alone, you have a 97% chance of detecting a 2.5 standard error shift or more within 10 subgroups. Rules 1 and 2, or rules 1 and 4, it doesn't matter which you pick next, give you this second curve. Rules 1, 2, and 3 give you the third curve. 1, 2, 3, and 4 give you the fourth curve. You notice how they're getting closer together? That's diminishing return. Adding more detection rules, there's a limit to what you can do to the power. The only way to move the power curve into this zone is by increasing your false alarm rate, letting the intercept creep up. So what does this mean? Well, that's the next slide. Rules used. Western Electric Rule 1, a point outside 3 sigma limits. 97% chance of detecting a large shift, a 50% chance of detecting an intermediate shift. Rules 1 and 2, or rules 1 and 4. And before we had computers, everybody kind of used rules 1 and 4 because they didn't require any calculation. This is 8 in a row. And this is a point outside the limits. So these are the two that are easiest to apply in practice without even any calculation. And so most of the practitioners were using these two. You got a 100% chance of detecting a large shift and an 80% chance of detecting an intermediate shift. You add rules 1, 2, 3, or 1, 2, 3, and 4, you can't increase the probability of detecting a big shift. You just increase the probability of detecting an intermediate shift. And frankly, you don't need that. You've got to have enough big shifts to keep you busy. When looking for signals of change that are large enough to guarantee that it will be economical to discover the assignable causes of exceptional variation, and to make these assignable causes part of the set of control process inputs, Rule 1 is sufficient. Keep the other detection rules in your hip pocket. If you see a pattern, you see something that looks suspicious, you can pull them out. And if you qualify with Rule 2 or Rule 3 or Rule 4, you've got a hunting license, go hunt. But you don't need to use them routinely. Rule 1 is going to give you most of what you need. So go easy on the detection rules. That's why I say turn them off. Let your eye do the work. Here's a chart from a chemical plant, 850 batches. They were computing limits every 100 every 100 batches, whether they needed to or not. Now, the limits are all over the face of the earth, but so is the process. I don't care which set of limits you pick, the story remains the same. This is an unpredictable process, isn't it? Now, because this piece of software focused on detection rules, it marked the long runs around the central line, but it didn't mark the points outside the limits, I guess thinking they're self-evident. They didn't make any progress because they weren't reacting to the real signals, because they were letting the software tell them what to react to. The software doesn't know your context. The software can't. Let the software create the charts. Don't let the software interpret the charts. You have to interpret the charts in context. And that's what software cannot do for you.
Now we come to the heart of the course. Section 5.3 of Understanding SPC is the key to the way of thinking that makes the process behavior chart come to life. Participants are encouraged to study sections 5.3 and 5.4 of the text until they become clear.
You have to make the chart work for you. You have to understand what the chart's doing. The average chart asks the question, are there detectable differences between the subgroup averages? The range chart asks the question, is the variation within subgroups consistent from subgroup to subgroup? We have to utilize that structure when we put the data in a chart. So we're going to use an example here on page 102. To illustrate different ways of organizing the data and the different questions they ask. This is a ball joint socket seat. This was used to be made out of pressed graphite. They're shifting over to make it out of injection molded nylon at this time. So you're changing the material and the fabrication technology. And when you do that, you have to do a certification run because you do not want to shut down an assembly plant because you can't make this 25-cent part. So the supervisor is going to collect the data. They have one mold and they run on one press with one operator on one shift. Now this press is a big press. They used to make dashboard inserts on this press. Now they're going to make 4 little ball joint sockets. So 4 times each day, the supervisor, Dave, goes out to the press, and for each of 5 consecutive cycles of the press, bang, 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 he gets all 4 parts, all 4 cavities, 1, 2, 3, 4, before they're knocked apart. He puts them on a cookie sheet, carries it back to his office, and sits down and measures the thickness. This is the distance from the center of the ball joint stud to the bottom of the ball joint socket. It's a virtual dimension. You have a special jig to measure it. And so 15 is 15 hundredths of a millimeter above the minimum spec. 10 is 10 hundredths of a millimeter above the minimum spec. So it's the 0 is just the minimum spec point. That's what's being recorded. So that's the data. So each hour he goes out there, each time, each visit, I call it hour here, is really visit. Each visit he has 5 cycles and 4 cavities. And the data are given starting on page 103. So we're on page 103 in Understanding SPC. We have hour to hour to hour. So each block is a different hour. We have cycles, A, B, C, D, E. And we have cavities. One, two, three, four. Stop before I get to the average. Now, to understand any organization, you have to understand the relationship between the sources of variation and the subgrouping used. Until you understand the relationship between the sources of variation and the subgrouping, you don't know what you're looking at. So we're going to practice this a little bit. Tell me about the context for this number. Hour 2, cycle E, cavity 4. Tell me about the context for that number. Hour
3.
3, cycle, E, cavity 4.
4.
Now, in this organization, my subgroup size is 4. I have 100 subgroups of size 4. So, are these two numbers in the same subgroup or different subgroups? Two choice, multiple guess.
Different.
They're different subgroups. When I change hours, I mean, they're different by hour, right? I didn't say that. These are different hours, and they're in different subgroups. Should have written the hours down. So when I change hours, I'm changing subgroups. Different hours correspond to different subgroups. So my hour to hour differences will show up between the subgroups. Every one of those statements started on the sources and ended up with the subgroup. Hour to hour differences show up between the subgroups. When I change hours, I'm changing subgroups. Different hours correspond to different subgroups. Okay. I'll miss that one. The two numbers there that are 14, I just drew a circle across the top of it. But how do those two numbers differ in context?
Same hour, different subgroups.
Well, they're in context. Subgroups are not context.
Okay.
Different cycles.
Different cycles. When I change cycles, am I changing subgroups?
Yes.
Yes. Look back over here. So different cycles, different subgroups. When I change cycles, I'm changing subgroups. So my cycle to cycle differences are going to show up between the subgroups. Okay. Here are a couple of numbers down here. How do these two numbers differ in context?
Same subgroup, different cavities.
Yes, they're different cavities. And so the difference in cavity is the difference in context. They are in the same subgroup. So my cavity to cavity differences are going to show up where?
Within the subgroup.
Within the subgroup. Can't get it all on the screen, but cavity to cavity differences show up. within the subgroup. So that's the organization we're looking at. And I repeat the organization here in the middle of page 104, what shows up between, what shows up within, and the chart is on the bottom of page 104. Is this process being operated predictably? Or no points outside the limits?
But you have a lot of points, consecutive points that fall on one side of above or below the average. And then
This thing doesn't pass the smell test.
Yeah.
It stinks, doesn't it? You've got 19 out of 20 at the beginning that are at or above the central line, or 20 out of 20 that are at or above, followed by 19 out of 20 below the central line. Now, I left some gaps here, and those gaps make it easy for your eye to find an anchor. It's hour 1, A, B, C, D, E, hour 2, A, B, C, D, E, hour 3, A, B, C, D, E, hour 4, A, B, C, D, E, etc. How many times did Dave go out there each day? I mean, I've told you, he went out there 4 times each day. So the first 4 segments are day 1. The next 4 segments are day 2, and something changed between day 1 and day 2, didn't it? In fact, the line segments I left out are some of the bigger line segments. Hour to hour and day to day, there's something happening to this process. And see, rule 3 and rule 4 catch it. You've got 12 below the central line here. You've got 4 out of 5 more than 1 sigma here. I put a point where you can see where I am. So you've got detection rule 3 and detection rule 4 and detection rule 3. I think you got rule 4 there too. You got all, so you see something suspicious, pull those detection rules out, and if you satisfy one of them, you've got a license to start looking for something. This is the first organization. The second organization of these data is shown on page 105. A subgroup is size 5. And it's each row. So n equals to 5, and k is 80. Same 400 data. Instead of 100 subgroups of size 4, we have 80 subgroups of size 5. So we want to go through the same song and dance with regard to our sources of variation and the subgrouping we have here. So I'll move up to the top of the page again. These 2 numbers differ in context in that they represent different hours. Are they in the same subgroup or different subgroups here?
Sorry, different subgroups.
They're in different subgroups. Subgroup is 5 values only, say. So my hour-to-hour differences are going to show up between or within the subgroups.
Between.
Between. Okay, I found a couple that are the same. These two values differ by cycle. Are they in same subgroup or different subgroups?
Same subgroup.
They're in the same subgroup here. So my cycle to cycle differences are going to show up between or within.
Cycle to cycle.
When I
Within.
change cycles, am I changing subgroups? No. Different cycles are in the same subgroup. So my cycle to cycle differences are going to show up within the subgroup. A, B, C, D, E in the same subgroup. Now, that's 6, that's 6. Differ in what way? In context. Well, they're different cavities. Are they in the same subgroup or different subgroups?
Different subgroups.
They're in different subgroups. So my cavity to cavity difference is going to show up between or within?
Between.
Between. The chart for this organization is at the top of page 106. If I'd just shown you page 104 and 106, would you have thought they came from the same data? I mean, you don't even need limits here. You've got a 4-point pattern that repeats itself 20 times in a row. You could march to this sucker, couldn't you? Hut, 2, 3, 4. So how would you interpret this chart? What's the pattern telling us? Cavity 1 is thicker than the others. And there's no question about that. Why did we not see that on page 104? Where were the cavity to cavity differences on page 104?
Was within the subgroups.
Buried within. Yes. Dave, the supervisor, did not use either one of these. He used the third organization. And those use the subgroups on page 107. Now, it's the same subgroups as we had on page 105. A subgroup, cycle A, B, C, D, E. So our subgroups are still 5, n equal 5, but we have k equal to 20. He organized them by cavity, a separate chart for each cavity. So when we compare, pick a value here with a value here, these two numbers differ. Now hour is out here in the front. So these two numbers differ by hour. Are they in the same subgroup or different subgroups?
Same subgroup.
And different.
You got two answers to a two-choice multiple guess.
But they're in the same cavity. Oh no, I've got the cavities the wrong way around.
Yeah,
Sorry.
they're the same cycle, but they're in different hours and they're in different subgroups because the subgroups are running horizontal here. So they're in different subgroups. So they're going to show up between or within.
Between.
Between. Well, look at spell. Between. So which chart will they show up on? The average chart looks for differences between, while the range chart checks for consistency within.
So they'll show up on the average chart.
So they'll show up on the average chart. Come down here. Okay. These two numbers are different cycles. They're in the same subgroup or different subgroups.
The same.
Same. So their cycle to cycle differences are going to show up between or within.
Within.
Within. So what part of the chart will show the cycle to cycle differences?
The range chart.
Range chart. Until you have this linkage, this source of variation will show up here and this source of variation will show up there. You really don't know what you're looking at. And what about, let's say, this difference from here to here? How do those two numbers differ in context?
Those will be on different charts.
Yeah, they are. The context is they're different cavities. So the cavities show up between charts. Dave showed me the charts and said, I don't know what to do about getting this process in control. I've never gotten a process in control before. But I know what to do about cavity 1, by gum. The specs are 0 to 15. So cavity 1 is making all of the non-conforming product. So he wanted to move the average for cavity 1 down about 7.5 hundredths of a millimeter, which is 3/3000ths of an inch. And he wanted to pull the average for cavity 2 down. He wanted to leave the cavities 3 and 4 alone because they're already pretty well centered in the specs. So he sent the mold down to the tool room and said, give me a 3,000th inch shim behind cavity 1 and give me a 1,000th inch shim behind cavity 2. That made sense. He got the mold back from the tool room, put it back on the same press, run with the same operator, and it was still unpredictable, just like page 108. But that wasn't what he was looking at. He wanted to see how much the central lines had shifted. And the central line for cavity 1 went down 5,000ths of an inch. The central line for cavity 2 went down 3,000ths of an inch. The central line for cavity 3 went down 1,000th of an inch. And the central line for cavity 4 went down 2,000ths of an inch. He went back down to the tool room. What'd you do to my mold? Everything's thinner. Well, I put a 3,000th inch shim behind cavity 1, and I put a 1,000th inch shim behind cavity 2. Is that what you wanted? That's exactly what I wanted, but everything's thinner. You do anything else to it? Oh, I cleaned it up for you. What do you mean you cleaned it up? Oh, it was covered in wax. I got it nice and clean for you. And Dave said, that's when the light bulb goes on. They used to make big parts with loose tolerances, and they spray mold release in there so the parts don't stick. You know, Baker's Joy or something like that, Pam. And they're still spraying it on this little mold that's no bigger than this. And so a lot of the wax is on the face of the mold, and as the wax builds up, the parts get thicker. And then they rub it down and the parts get thinner, and then the wax builds up. So the day-to-day and hour-to-hour problem you see back here on page 104 and on page 108, that's the wax buildup problem that they hadn't figured out how to master. So they've done something to make the 4 cavities alike, and they've taken care of this problem of wax buildup. And so 6 months later, I'm walking through that area of the plant. Dave sees me, grabs me, pulls me into his office, and hands me this chart here on page 110. Now, the operator is keeping the chart. Which of the 3 organizations we've looked at is this most similar to? Is this similar to page 104, 106, or 108? How is it similar?
It's like page 104, I think.
It's like page 104 in that it has
It's all the averages.
all 4 cavities combined inside each subgroup. That was a problem back on page 104, wasn't it? Here, the cavity to cavity difference shows up on the range chart, and the average range is 7.9. On page 110, the cavity to cavity differences show up on the range chart, but the average range is 3.7 and the upper limit is 8.5. That's almost the central line on page 104.
So they've massively reduced the variability.
Yes. This is not a good practice to put parallel operations in the same subgroup, but they get away with it here because they made the parallel operations alike. And now they can subgroup them together for the convenience of the operator. He has to open the cage and grab a piece or a set of 4 pieces and then close the cage back. And it's easier to do one set of 4 than do it any other way. He's got other jobs, other things he has to do. So it's more convenient for the operator this way. See, this is not the certification run. This is operational. And different persons collecting the data for a different purpose. Notice the date. They just came back from the Christmas shutdown. And so they get a piece every hour. They're running 1 shift a day still. On January 5 and January 6, or January 3 and 4. And then on the 5th, 6th, and 7th, they get once in the morning, once in the afternoon, once in the morning, once. They don't need a lot of sampling because this process is running very predictably. And so they back off on their sample frequency. You see how you collect the data, who charts the data, what purpose you're collecting the data for, and how you organize the data all depends on the context. And when the context changes, some of those things can be changed. So while this is not the best, generally, not the best practice in general, it works here because they made the 4 cavities alike. Now, how can I say the 4 cavities are alike still? Well, if we got a cavity that started going bad, you get a big range, wouldn't you? I'll go back to page 106. On page 106, the cavity-to-cavity differences are between, and the hour-to-hour differences are between. The only thing that is within is cycle to cycle to cycle. What's the average cycle to cycle range? 3.5. That's the average difference shot to shot in the same cavity. Now go back to page 110. When we get the cavity to cavity difference, 3.71 on the average, down the same size as the shot variation, 3.5. We've gone about as far as we can go in making the cavities alike, haven't we? You see, subgrouping is an art. And the different subgroupings we've looked at ask different questions of the data. And if you don't control those questions, you end up asking the wrong questions or not getting the answers you need. So how you allocate the sources of variation to the subgroups and where they show up on the chart is the secret of understanding any average and range chart. Now I'm going to make a suggestion. Subgrouping requires careful thought and practice. You don't get good at this except by practice, and we're going to practice it in the examples that follow. One person told me that page 100 to 115 was the heart of the book, and I think he's right. Page 100 to 115, David Chambers would assign that these last two sections in chapter 5 were to be read every night. Read it and read it again until it makes sense, and read it one more time. Keep reading. Now I'm going to make a suggestion. If you're not sure about the subgrouping, it's hard to screw up the subgrouping on an XMR chart. Every point has to sink or swim on its own. So if you're not sure, do like the Creel yield data. Put them on an XMR chart and see what happens.
To summarize the lessons of Section 5.3 of Understanding SPC, we now turn to the principles of rational subgrouping covered in Section 5.4. But first, we will consider Exercise 5.2 on page 116.
This was a little process trial. 10 pieces of brake lining, piece A, B, C, D, E, F, G, H, I, J. 10 pieces of brake lining from the same batch cooked in the same cavity are measured, and they're going to measure the thickness at 8 positions as identified by the drawing. And one of the questions of interest here is the average end thickness the same at the hinge end as it is at the clamp end of the cavity. So if we take these data and do 10 subgroups of size 8, we get this chart. Will this chart answer the question, is there a detectable difference between the average end thicknesses?
No,
Correct.
it's a grouping by piece. You have
Because
to group by the
two
position.
ends are subgrouped together, aren't they?
Yeah.
So how would you reorganize the data to answer that question?
You'd have to have 8 groups of 10.
Well, that's one solution, 8 groups of size 10. And when you do that, you get this chart. Positions 1 and 2 are thin, and 6 and 8 are thick. There are other organizations as well. A traditional t-test would take the 1, 2, 3 and the 6, 7, 8 and two subgroups of size 30. There's your traditional t-test. These two subgroupings assume that the 10 pieces are alike. So if you wanted to examine that, you might use 20 subgroups of size 3. When you do that, you've got 10 in a row below. Now, for this example, I organized them by hinge in and clamp in. Didn't put them in a strict time order. So it's A, B, C, D, E, F, G, H, I, J, K, or J for the hinge in, then the same for the clamp in. And you've got 10 below and 9 out of 10 above. Yeah, they're different. No question about it. You see, you got to organize the data to allow the questions of interest to get addressed. So let's go page 112 in the textbook. Questions regarding data. When you organize your data onto a chart, these are questions you need to ask yourself, because these are questions you need to be able to answer when other people ask you about your chart. What do the individual values represent? What are these numbers? How are the values obtained? Who obtains them? How often? At what location? By what method? With what instrument? What sources of variation are present in these data? And only then are you ready to start talking about the subgrouping. What sources of variation occur between the subgroups, and what sources of variation occur within the subgroup? And finally, do you have any expectations for these data? Are these data that ought to pile up against the boundary condition? Is there some limitation on the range of values that you expect to see and you look at the histogram? What is the background? These are questions that are important when you start subgrouping. Now, subgrouping principle number 1, never knowingly subgroup unlike things together. Apples and oranges and bananas make great fruit salad, but they're lousy subgroups. What happens if I accidentally subgroup unlike things together? Well, you're going to have page 1, something like the top of page 113. Look at this range chart. This is the range chart from page 104. And I've highlighted a white, or you have it white, though the yellow band here on the screen is plus or minus 1 sigma. How many points are inside that band? It's easier to count how many are outside the band.
5 outside.
95 out of 100, literally, are inside the band. 95 out of 100 is a 2 sigma number, isn't it? Not a 1 sigma number. This is too good to be true. The phenomenon known as hugging the central line. When 15 or more successive values fall within 1 sigma of the central line on a range chart, it's appropriate to check for possible stratification within the subgroup. Here is what you would expect to see on a range chart for subgroups of size 4 with an average like 3.9, and you get 95 out of 100 within 2 sigma of the central line. But in answer to your question here, what happens when we add 4 to every value in the ranges? Well, that puts all the ranges up on stilts. The average becomes 7.9, and the upper limit gets blown up, and we have 95 out of 100 looking like they fall within 1 sigma of the central line. And it's this constant difference that occurs inside each subgroup. And that's what we get out of stratification. You see, in this case, cavity 1 and cavity 3 were really different. And most of the time, that difference was around 4 units. And so most of the ranges have been inflated by 4 units. And we have this hugging the central line phenomenon. Stratification, which is improper subgrouping, where unlike things are subgrouped together, can create this phenomenon. In fact, on the first chart for the break lining parts, look at the average and range chart. Look, you can hardly see the central line. We only have 10 subgroups here, but still, you see the hugging the central line and hugging the central line, and you've got what you know. You see on the very next graph are differences. The 8 positions have appreciably different averages, and those differences create the stratification. The stratification manifests itself with charts where everything's hugging the central line. When you take administrative and service sector data and try to put them on an average chart, most of the time you run up into stratification because your subgroups, you're subgrouping unlike things together. In Schuhart's second book, he actually put it this way: when we put 2 numbers together in the same subgroup, we're making a judgment call that those 2 numbers were collected under essentially the same conditions. So, subgrouping principle number 2, minimize the variation within each subgroup. It's the variation inside the subgroups that creates the estimate of routine variation that you use to filter out the noise. Subgrouping principle number 3, maximize the opportunity for variation between the subgroups. If 2 things might be different, they belong in different subgroups. Because if you put them in the same subgroup, you're assuming they are the same. You put them in different subgroups, you're allowing them to differ. Average across noise, not across signals. When you start burying the signals in the chart, you get a chart like page 104. Look at the width of the limits on the X chart, on the X bar chart, on page 104. Four to 15, 16. Now look at the width of the limits on page 106. 8 to 12. When we had all 4 cavities in the same subgroup and the 4 cavities were different, it desensitized the chart. You want to avoid that. Don't bury the signals. Treat the chart in accordance with the use of the data. As the person keeping the chart and the purpose for the chart and the knowledge we've gained changes, you may need to change your subgrouping or even go to a different type of chart. So it's not fixed in stone. Rational subgrouping is an art. Now, when you're talking about a chart for individual values, you need values that are logically comparable. You've got to be apples to apples, not apples to orange. Well, that's rational subgrouping.